Hi, we're a team of Faris, Jason, Rajveer, and Teague, four developers from Oregon State University. And our app is called LiDAR to 3D Sound Application for Hearing Impaired. Over 285 million people worldwide are visually impaired, and for them, navigating everyday spaces can be dangerous. Traditional tools like white canes can only reach 1 to 2 meters ahead. So we built an app that turns your iPhone into a navigation aid. Using the built-in LiDAR sensor, we scan the environment 60 times per second and convert obstacles into 3D spatial audio. Objects to your left play in your left ear, objects to your right in your right ear, and the closer they get, the faster the warning. It's completely hands-free with voice control, letting users hear their surroundings. Hi, I'm Rajveer. My main contributions were LiDAR data capture, point cloud processing, 3D visualization, voice control, and sonification redesign, built with ARKit, SceneKit, the phase framework, and speech framework. This screen on the right side, you can see that the app is installed on my iPhone. The logo was also designed by me. If I open the application, you can see that this screen shows my
Voice
LiDAR
control active.
capture manager in action. ARKit is the only way to access the LiDAR sensor on iOS. You can see the stats basically confirm that it's a LiDAR session is running, and you can see that it's taking in basically around this many frames, and it's processing this many points per frame and the average distance, all these stats. The development flow basically started with setting up MVVM architecture, then building the ARKit capture manager. Each frame I'm taking raw depth values and converting them into 3D world coordinates using combined publishers to stream data reactively between components. If you look at over here, this is the PLY export system that I built for a teammate who didn't have a physical iPhone device. And this is basically I export the data, and so you can test it out without a hardware. I also built this 3D debug visualization tool with SceneKit. Uh, with this, you can actually see the point cloud. You can actually see the visualization of the point cloud and the detected object as boxes, as bounding boxes with varying shapes. Uh, and then the sonification engine was also built, reworked by me. If you The original plan was a continuous audio tones, uh, increasing in volume, but testing showed that it was overwhelming, so I redesigned it with zone-based beeping, which immediate, near, and far zones, where silence means clear path. If I move my phone towards an object, you can see that it's
Obstacle
beeping.
very close to your left.
Closer objects trigger faster
clearing.
and higher pitched beeps. Clear path means no audio, which is much more intuitive. Audio is spatialized using phase. The beep comes in from the direction of the obstacles. Um, Another challenge I had to face was I had to fix the phase listener to follow the camera transform to get this working. Uh, Basically, the key lessons I take from there is that the AR coordinate systems
Obstacle
where
4.8 meters
one
to your
wrong
left.
sign breaks
Path
everything
clearing.
silently. Real-time 60 FPS processing requires background threading, and most importantly, you have to measure first, optimize second.
Hi, my name is Jason Tang, and my main role in this project over the quarter is to create a spatial analysis manager for both Rio and mock data, detected objects and proximity zones, object tracking, persistent object IDs, and a tutorial section. These are the technologies and frameworks I used and the development steps I took. So now I want to demo my portion of the app, which is hosted on a virtual Mac environment. Here we can see the app takes in both real live and mock test data in the form of a PLY file, which contains the x, y, z coordinates and depth of a point cloud. So if I load this specific file, then it shows that I have 1325 points with an average distance of 0.2 meters. And then if I load this one, then it's a different amount of points and a different amount So next I want to demo the tutorial, which is in this more section of the UI. So it shows a basic welcome page, an explanation of how it works, a getting started page, proximity zones explaining what you'll see when you use this, or what you'll hear specifically. Page on object classification, walls, floors, ceilings, or obstacles. Safety page, customization for each individual, and finally a ready page. So the original plan was that I successfully implemented the Spatial Analysis Manager and Detected Objects modules, which forms the backbone of the spatial analysis. The grid partitioning and clustering was also completed, and a few things I deviated from was the object tracking method to maintain persistent object IDs. We used a 50 centimeter position proximity threshold to prevent audio flickering, and I included this tutorial system user interface to help the user. A few challenges and solutions. There was some memory management with large point clouds. The solution was to implement grid partitioning and clustering techniques to reduce memory footprint and processing overhead. And another one was just auto flickering from frame to frame object ID changes. So that one was pretty simple. We just developed a object tracking system that matched objects between frames using position proximity. So what I mainly learned was gaining hands-on experience with using Apple apps and products with a clear separation between the and the VM models. And I learned techniques for processing point cloud data, including grid-based spatial partitioning and object clustering algorithms, and just workflow between the different modules, the LiDAR acquisition, spatial analysis, and sonification.
Hey, this is Teague, and here are my contributions to the project. My main roles included building the audio playground for testing spatial audio in the app, then turning that into the sonification engine, which turned our list of detected objects into spatial audio, and I also did some R&D exploration of how to detect those objects. The technologies I worked with were the two spatial audio iOS APIs, AV Foundation and the Phase Framework, as well as ARKit for reading LiDAR sensor data, and I also experimented with RealityKit as an alternative rendering library. My development started with prototyping spatial audio to prove that our project could fundamentally work. And then I promoted that to an audio playground view. The audio playgrounds simulated an iPhone user from side and front views and let us move a simulated audio source around the front of the phone. This was useful for testing out spatial audio in headphones. I soon realized that there is a new audio framework called Phase, designed for AR specifically, so I migrated the code to use Phase. And then evolved that code into our sonification engine, which would glue together object data and audio. During my R&D phase, I looked into 3 different solutions. First, I tried using the built-in AR mesh anchor and AR plane anchor that ARKit provide. ARKit fires off callbacks for newly detected objects and planes. We ultimately gave up on it because it couldn't handle dimly lit rooms. The next method was using collision objects. Then we discovered that ARKit provides a real-time list of collision objects, which are the gray spheres seen here. This ultimately failed because collisions in the walls weren't well supported. And the third method I explored was using the built-in LiDAR mesh data. The mesh data derived from LiDAR was impressive, but ultimately didn't provide any benefit over the raw LiDAR point cloud data that we already used. The biggest change from our project plan for me was the audio framework. Our original plan was to use AV Audio Engine, but we later realized that the Phase framework was perfect for our application. Some challenges that I ran into included simulating the spatial audio on an iPhone, which led to the audio playground, having too much audio boilerplate code, which was fixed by switching to the Phase framework, and a slow app boot up, which I partly addressed by parallelizing some static file loading. And some things I learned during this project included the concept of camera intrinsics, the difference between AV Foundation and the Phase framework, the difference between SceneKit and RealityKit, rendering APIs, and finally how data bindings are typically done in iOS using the combined framework. Thanks.
Hi, my name is Hossan, and this is my team contribution. My main responsibility was the UI UX for the project, and I was also responsible for implementing some accessibility features and testing with some CI and debugging. We chose Swift UI because it integrates pretty seamlessly with modern Swift features and Apple frameworks. It has built-in solutions for managing UI and state, and has declarative syntax, which makes it concise and easy to read and handles complex layouts and system features. As a bonus, we get Xcode canvassed for quick testing. The first step was to create a base UI from the mocks that we had in our development plan, and I used state variables so Swift UI could manage the state at first. That way I could iterate quickly and test and develop and see the feel and look of the app. I also iterated by adding accessibility features like haptic feedback, voiceover integration, high contrast, and dynamic types. Then I created an MVVM structure to bridge the model and the view by exposing data from the models as properties. Originally, our team was divided evenly between sonification and LiDAR capture analysis, but we decided that it was important to have the UI completed first with accessibility features, so I decided to wholly focus my attention on that. We faced some challenges along the way, like when we wanted to optimize object detection. It took us a while to get the debug visualization working, but we found a working solution eventually through some debugging. And this led to delays in the UI, and also testing voiceover was hard. I learned a lot from the development of this app. I got familiar with iOS development, the Swift language, and Apple libraries and frameworks. I learned some vital lessons in state management and concurrency. And using the MVVM structure, it made it easier to track down bugs and related data changes because the view is simply a passive reflection of the view model state. And in the end, building the app step by step, I learned how to develop scalable software by focusing on building and testing contained pieces of functionality. Here's a quick demo of my Swift UI implementation. All the buttons and toggles and sliders are functional and provide haptic feedback for confirmation of a change. Within each section, there are accessibility hints describing the functionality and interactions. At the bottom, there's a tab menu that allows you to switch views. And the UI is designed with high contrast and voiceover support.
Where does this go from here? We'd love to add machine learning to identify what objects are, not just that something is ahead, but chair or person approaching. GPS integration could enable full outdoor navigation, and Apple Watch haptics could provide silent cues in quiet spaces. The app could be open sourced as free accessibility tool or developed further for the Apple Store. We want to thank Oregon State University and our CS 467 instructors for this opportunity. We believe technology should be accessible to everyone, and this is our contribution toward that goal. Thank you for watching.